These are also referred to as double replacement. Reactions in some textbooks. And empirically, the ions exchange positions. AX plus BY goes to AY plus BX. And you can draw brackets between, say, A and Y, and then X and B, and you can see that exchange from the reactant side to the product side. Now, some characteristics of a metathesis double replacement reaction is, one, the oxidation states do not change for the elements. That is, if it's a +1 on the reactant side, it's going to be a +1 on the product side. -1 on the reactant side, -1 on the product side, and so forth. The driving force of the reaction, that is, the force or process that pulls it to completion, can take one of three forms. An insoluble precipitant, abbreviated PPT, a weak acid or weak base, or a gas decomposition product. Regardless of which one it is, the driving force is the tendency toward a more stable compound. Now, when we talk about a more stable compound, you need to understand more stable means stronger bonds. That refers to A and B coming together to form a stronger bond on the product side than something else on the reactant side, which has weaker bonds. So, more stable, to clarify, refers to formation of stronger bonds or chemical bonds. In a typical double replacement, I'll just give you an example, HCl plus NaOH, we find the ions in this structure, in this example. This is the AX plus BY, and so we want to take the A and Y and hook them up as a product, and a BX and hook them up as a product. And of course, you would list it conventionally, plus ion followed by the negative ion, the anion. So what I'm showing you here, and I'll take sodium chloride first, so we hook up NaCl, which is a +1 - 1, so that's the proper ratio, plus H And I'm going to write water in this format, like that, where over here you see the OH group carrying a -1 charge, +1, -1, +1. These, the hydrogen and the oxygen, would connect here, and this is a strong bond than anything on the reactant side. The HCl has a very weak bond, sodium and hydroxide, very weak bond, and it drives to a salt, which in itself has a fairly weak bond in this case. But the driving force is identified because hydrogen is connected to the OH with a stronger bond than it would be hydrogen connected to chloride. So this is the identified as a driving force. Just to illustrate the idea of, well, what is a driving force? It's a tendency to form a stronger bond. Now, again, the types of driving force are insoluble precipitant, a weak acid, weak base, or gas decomposition. Now, this little table will be attached to your exam, and you can use it to determine the driving force of a metathesis reaction. And it's divided into 3 parts. Remember I said that the driving force can take 3 forms. It can become an insoluble precipitant, or it can be a weak acid, a weak base, or a gas decomp. And that's the way I have this. In this portion right here, these are precipitants driving forces. The strong weak acid issue are your weak acids, weak base. And down here is your gas decomps. So in the examples I'm about to use, and we will going to work through the worksheet, you will hopefully see how this table is used. Now, we'll begin with the insoluble precipitant driving force in the metathesis. So one of the emphasis here is you are looking for something on the product side. Driving force is always on the product side, incidentally. Looking for something on the product side that is a precipitant, insoluble precipitant. Soluble means it's not a driving force. On this page, and it should be the last 2 pages or somewhere in the handout. So we'll work through each one of these to show you how to deal with the metathesis double replacements. Okay, so we want to write out, the first one looks like iron chloride and sodium hydroxide. So we'll start out with the iron chloride. Now these are typically in an aqueous solution. HU means that they are dissolved salts and have ionized. Plus the sodium hydroxide, and that's also in an aqueous. And then you write the products. Now, we're going to have 3 kinds of equations. The first one is a molecular equation, where everything's in sum of charges equals 0 and reduced to the molecular forms. Now, in predicting the outcome, remember AX plus BY goes to AY plus BX. So you need to identify the ions in the reactant side. And you recall what I told you yesterday about identifying where the polyions are and where the cations, anions. From left to right in any compound, mentally separate the first metal from the rest of the molecule, and this is your cation. And chloride is your anion. Over here, you take the first metal, separate it from the rest of the molecule, and sodium is your cation, hydroxide is the polyion on the right side. Now, in the process of writing the products, we want to connect the outside ions and then the inside ions like that. And so what we have is an iron hydroxide and a sodium chloride. I'll put sodium chloride first. And the first thing you do is just put the two elements or polyions together without anything else. You may already know what's going on. But first you connect them. Now, because I want to emphasize something here about the subscript on the left, that's chloride, you won't have a subscript here. Just because now listen to me, just because there's a subscript of 2 on the left doesn't mean you'll have a subscript of 2 on the right. The ratio of elements in the compounds depends on sum of charges equals 0. So +1, -1, sodium chloride doesn't need any subscripts. However, when you look over here, -1 has to be multiplied by 2. And so iron is a +2 to get some of, so this would be a -1, -2 net charge there. -2 + 2 gives you 0. So this is the correct ratio for the iron chloride. But when you form the product side, it's 1 to 1. Same way with the iron hydroxide. The hydroxide is a -1, iron's still a +2. Remember, from the left side to the right, you don't change the oxidation state. So an OH over here being a -1 is going to be a -1 over here. So I have to put a parentheses 2 hydroxides. And I want to find out which of the 2 compounds on the product side are driving forces. One of them will be and one of them will not be. So using the table now, remember I said the top 2 tables are dealing with the precipitant or non-precipitant in here. So what should we do here? Well, we want to take the first compound and look at it. This is a chloride. That's a halogen. A halogen salt is what this is. So we have a sodium chloride. So we want to look over here in our columns over here and see if we have any halides. Well, halides are right here in the first one in our list. And what this says is that see it's at the top of the heading, it says soluble. That means everything in that column is soluble. And then it comes over to the right, exceptions. These are exceptions to solubility. Well, what's an exception to solubility? That means it's insoluble and yes, will be a driving force. Halides have to be mercury, silver, or lead halides. One of these 3 in order to be a driving force, a precipitant. Well, sodium is not one of those 3. So sodium chloride is soluble. And therefore not a driving force. So if it's not a driving force, it remains in solution in ionic form, floats around in sodium and chloride ions. So since we've excluded that one as a driving force, we need to go over here to the next compound, the iron hydroxide, and look at it. And we look down here and we see hydroxides as in the second table. Well, all hydroxides in the universe are insoluble in general, except group 1A. Well, what's the group 1A? That's your group 1A, lithium, sodium, potassium, rubidium, cesium, francium, that kind of collection. So if we have one of those attached to an OH, it's soluble, because those are the exceptions over here. And ammonium salts, ammonium hydroxides, barium and strontium hydroxides are soluble, and they will not be driving forces. That is, if this was a barium hydroxide or strontium hydroxide or an ammonium hydroxide or lithium hydroxide on that, not a driving force. However, if it's not a member of the exceptions, all hydroxides are insoluble and therefore insoluble, and therefore is a driving force. So this is the iron hydroxide is the driving force that pulls the reaction to completion. Now, of course, if it's not balanced, we want to balance it. You probably balance it before you make a decision on driving forces. So we have to have 2 hydroxides on the left, 2 sodiums here, and that will balance the reaction. So there's your balanced molecular reaction there. I'll clean it up some so you can see it in total. This is AQ plus 2NaOH. AQ goes to 2NaCl. That should be listed. As not a driving force, it stays in solution, AQ. And then we designate the iron hydroxide as a solid, and that indicates that that is a precipitating solid coming out of solution. Everybody good? Yes, ma'am.
Does it matter which order you write them in?
What do you mean? Sodium hydroxide, iron?
On the other side of the arrow, does it matter if you put the iron hydroxide first? Or
No, it does not.
Okay.
I just like to put them on the end. I just feel better.
Okay.
It's really your preference. Okay, so these are molecular equations because everything's in molecular form. Now we need to look at ionic equations. Now everything that is tagged as an AQ ionic compound, that's a metal, non-metal. Metal and polyions are considered the non-metallic. Metal, non-metal, metal, non-metal. That's not a driving force. Driving forces are not written in the ionic form in the ionic equation. So this would not be written in ionic form. And what do I mean ionic form? The salts will break up in cations and anions. And so iron chloride would be written like this. It shows that when this goes into water, it breaks up into 1 iron plus 2 ion and 2 chloride ions. Well, same way with sodium hydroxide, except it has a coefficient of 2, and so it has 2 sodium ions plus 1 aqueous plus 2 hydroxide ions, and those are in solution also. And this yields, okay, so you have sodium chloride on the product side, and so you have 2 sodiums, aqueous, plus 2 chlorides, aqueous, plus 1 driving force, iron hydroxide, and we do not show it in ionic form. We leave it listed as a solid on the end. So this is your complete ionic equation. Now, the net ionic equation, which we write next, shows only those reagents that undergo reaction out of the net, out of the ionic equation. Shows only the reacting ions. The other ions are referred to as spectator ions. How do you find those? Well, if you look, you see sodium on the left and sodium ion on the right, as well as chloride and a chloride. These are spectator ions. Now, you can mentally do this kind of as like a math problem. Since they're on opposite sides and equal in amounts, coefficients, then you can cancel these out like that. The remaining ions and compounds are the reactive issues in that reaction. So when you write your final equation, net ionic equation, it is in this form. Like that. So those are driving forces for salt systems. Now I want to show you one other here. I'll make it up as I go. All right, we're going to work sodium sulfate and potassium bromide. And write the molecular equation and see if it's got what the driving force is. So again, we want to find the cations and the anions and exchange them and put them together so the sum of charges equals 0, right? So in this one, I'll move it over a little bit. Sodium sulfate plus potassium bromide. If I can write them for you. We'll go to sodium bromide plus the potassium sulfate. Now, sulfate's a -2, so we'll need a 2 on the potassium right there. Okay, if we need 2, we need to balance the equation. So I'll go ahead and balance it with a 2 in front of that one, and we need a 2 in front of the sodium bromide. So now we need to look at each one of the compounds on the product side, see if it's a precipitant or not. Only precipitants will generate our driving forces, and they'll come out of solution. So here's a sodium bromide. That's a halogen. So we look on our sheet and say all halides are soluble except mercury, silver, and lead. I call these the happy halides, HAP, mercury, silver, and lead. And so halides are, does this say mercury, silver, or lead? No. So sodium bromide is a soluble and therefore not a driving force. Everybody good? Okay. In the potassium sulfate, we look in here, all sulfates are soluble except barium, calcium, strontium, and lead. Well, this is not a barium, strontium, calcium, or lead. So it's a soluble also, and not a driving force. The point is, when you mix certain salts together, you may not get an outcome. And the way you would list this is no reaction. So this doesn't occur. So this gives a no reaction. So that's what I'm trying to point out to you. And one of these typically is a driving force and will conform to the table that you just looked at. However, some problems pop up on the exam, neither one of them. And so your answer choice would be no reactions occurring, something like that. On that second page, well, maybe not. I'll just make them up as I go along. It's the simplest thing. You can work those that are on the handout about as easy as I can give them out. Okay. In the world of acids and bases, begin with acids and bases are electrolytes. That means when put into water, they ionize and have the ability to conduct an electric charge. That's what electrolyte means. When we talk about the classes of electrolytes, you have two: strong electrolytes and weak electrolytes. And these are easily characterized in terms of strong electrolytes are 100% ionized, and weak electrolytes are less than 100% ionized. So when we apply these terminology to the acids and bases, we wind up with strong acids and weak acids, as well as strong bases and weak bases. So from a strong electrolytes, we get strong acids. Now, there are acids, inorganic acids, that are stronger than what I'm about to give you, but these are molecular acids, and there are only 6 strong molecular acids that ionize 100%. That is, you won't find any molecules of these compounds floating around with the ions. So the 6, I call them the strong 6. Or the strong acids include HCl, HBr, HI, HNO3, HClO4, and H2SO4, first ionization step. See, that's a polyprotic or diprotic acid, H2. So it ionizes in a couple of steps. It ionizes to get, well, I'll show you very quickly. H2SO4. First ionization step would be this. And then the second one, it has an ionizable hydrogen there and goes to H plus SO4 2 minus. So this is the first ionization. And second ionization. Now the first ionization step is what we're talking about here. You will not find any molecules of H2SO4 floating around in solution with the other ions in this. But the second step is a weak acid. This will be present with the ions that come from that acid, that weak acid. So that's just what it means. Now, what's the purpose of this is you memorize these with all due diligence. Because if you know the strong acids, you already know the weak acids. It doesn't matter if you know what it is. It's just not a member of the strong 6. That's the point. For example, given a problem which of the following is a weak acid: HCl, HNO3, HC2H3O2, and H2SO4. So you give an A, B, C, D like that. Now, if you know the strong acids up here, you can check those off, and the only one that's not a member of the strong acids is that one. You don't know what it is, you don't care what it is, but you know that that ain't part of that. And so that's how you tell the weak acids. Now again, when you're dealing with weak electrolytes, these will ionize 100%, prefer to be in 100% ionic form. but this one is less than 100% ionized, and you will find it in combination, it not only this molecule, but you'll find it in equilibrium with ions of its hydrogen and your C2H3O2 ion. So that's what the nature of a weak acid is. Weak bases, all I'm doing is defining what the acids and bases are right now. Weak bases are bases as electrolytes. Again, are strong bases and weak bases. The strong bases are very easy to remember. Group 1A and group 2A hydroxides. Except for beryllium. It's not one of that collection. We'll talk about that later. That's not one of the strong bases. So, potassium, sodium, rubidium, cesium, francium, 1-to-1 combinations with an OH. Calcium, magnesium, strontium. Those are 1-to-2 combinations, but when you throw them in water, they will ionize and you won't have any molecules of calcium hydroxide floating around in the solution with the ions. But a weak base will have the molecules as well as the ions together. So weak bases are of two kinds: ammonia or ammonia derivatives in water. Ammonia is a molecule that looks like this. Well, let me do it this way. H2N. H3N. It happens to have what we call a non-bonded pair of electrons attached to the nitrogen. And this has a very strong negative attraction. And it's called a partial charge symbol. Write an S with a little tail on the end of it like that. Put a negative superscript on it. That's called a partial negative charge, like that. Well, if you put that in close proximity to water, which you'll learn will have what we call a bent angular nature, the hydrogens in here have a strong positive charge right there, and there is a connection drawn together. It's called, a coordinate covalent bond. This pair of electrons will pair up attract to this positive charge right here. And the outcome will be like that. Well, this is ultimately translated into NH4OH, and which is the ammonium ion and the hydroxide ion, where this is +1, remember your polyion list, and OH is a -1. And when it breaks into two parts, the cation and the anion, it goes to NH4 plus OH minus, but is in an equilibrium with the molecule. So you'll have the molecule and the ammonium and hydroxide ions all floating around together. And so this is what constitutes the weak bases. Now, the derivatives are just the same process, except you take one of the hydrogens and you substitute some weird group on it. That's a derivative of ammonia. And this still reacts with water in the same way. And the outcome of this are in H3OH, with that part's plus, that part's minus, one-to-one ionization. And so that's where those come from, those base ionizations. So if I had methyl ammonium ion like this, methyl, it's called amines, methylamine plus H2O, it would just simply absorb one of the hydrogens into that structure, and you would have methyl ammonium hydroxide. Actually, that's a 2. That should be a 2 right there. So it absorbs 1, becomes 3OH. And so this part would be a +1, that's a -1 as they split. And then when they ionize, it's shown to be like this. And so that is a weak base. Okay, how does all that come together in the metathesis type reactions? Now, what I've just done is I've defined strong acids, strong bases, and weak bases. Strong acids, strong bases are not driving forces. Why? Because they can remain 100% ionized. You only find a weak acid or a weak base as the driving force, because when the hydrogens come together with the anion, it forms a stronger bond than what was on the reactant side. And the same way with bases. When the cation ammonium ion is in the presence of something that it forms a stronger bond, that's the driving force. If it forms an hydroxide, ammonium hydroxide or derivative hydroxide, it's a driving force. But if you have calcium hydroxide plus ammonium chloride, will it produce a driving force? Yeah, because ammonia and hydroxides will hook up. They're very strong attractions. On the weak side, weak electrolytes have strong bonds. Strong electrolytes have very weak bonds. So work on that. Earlier I used this one. And what's the outcome of that? Well, it's treated the same way as we did the precipitant reaction. We have to identify the AX and BY, exchange the ions, and so sodium and chloride would hook up. I'll come down here and do this. So sodium and chloride would hook up, and the hydrogen would transfer over to the hydroxide. I'll put it on the system like this. So looking at the product side, do we have a driving force? Well, if this is an acid-base reaction, what's going to happen is going to give a salt plus a weaker acid than you started with. It's just the way it is. Acid plus base gives salt and water, or acid plus base gives salt and a weak electrolyte. That's the way acid-base reactions proceed, all of them. Is that a weak acid there? Well, yeah. How do I know? It's not a member of the strong six. HCl, HBr, HIHNO3, HClO4, and H2SO4 first ionization step. So that's your driving force, is H2O. So that's the formation of that bond between hydrogen and the hydroxide is stronger than the bond between hydrogen and the chloride. So that's why that transfer takes place. And it's true for any system that will form a stronger bond. Now this is an acid because it has what is called an acidic hydrogen. Now one of the things about all of these acids is they have some anion. Let me do it that way. So this is called an acidic hydrogen and will break away from the anion and float around in solution. But that's how you identify an acid. Well, remember the precipitating salts, that was a metal, non-metal. That doesn't look like a metal at all. Hydrogen is not a metal. If you see that hydrogen, acid. Or if you see some kind of metal and an hydroxide hung on there, base. So you were trying to talk about, well, what are the driving forces in these metathesis reactions? They're in acids and bases, but they have to be weak acids and bases. Ammonia derivatives, or ammonia, or one of the weak acids, which are not a member of the strong six. So there's some logic there, but you can handle it. You put some time in on these ideas. Now let me show you some other, the idea. I want to say more about ionizable hydrogen. This is a table of what we call acid ionization constants, but what I want you to notice in this, all of these are preceded, all the formulas are preceded by hydrogens. You look down the collection here, everybody's got a hydrogen out there. Those are ionizable hydrogens. Those are the hydrogens that'll break away from the formula. If you're given a formula, this is one way it's written in molecular form. But you also have hydrogens that are not leading hydrogens. Those are non-ionic hydrogens. So C2H3O2 is an acetate ion, and those hydrogens in there are bound to the carbon so that they don't come off. So as you proceed in the idea of metathesis and you're studying driving forces and find a weak acid, you need to understand what part of that acid is going to fall off and what's not. So if it's written in this form, you can always count on that hydrogen out front as being the ionic hydrogen.